We will now narrow our focus to solving trigonometric equations with compositions over an interval. Here's the procedure. Find the complete solution to the trigonometric equation. That's what we've been practicing. Then we'll determine the specific solutions that satisfy the equation only in the given interval. Let's take a look at example 3. Find all solutions in the interval from 0 to 2 pi for each equation. Notice the grouping symbols on this interval. If we get 0 for a solution, we will include it in the solution set. However, if we get 2 pi, since it's coterminal with 0, we will not include it in the solution set. This interval also indicates that we should be solving the equation in radians. To begin solving the equation in example A, we need to isolate the trigonometric function. So we can add square root of 2 to both sides and then divide by 2. We'll obtain cosine of 2x equals square root of 2 over 2. At this time, we can isolate the argument by applying the inverse cosine to the other side. So 2x is equal to inverse cosine of square root of 2 over 2. Now remember, we have to be patient at this point. We're not going to isolate the variable until the very last step. Let's take a look at the unit circle and find all angles on the unit circle with a cosine of square root of 2 over 2. That's one of my favorite angles. Pi over 4 is generally easy to recognize and work with. So cosine is positive in quadrant 1, but we also need to recognize cosine is positive in quadrant 4. Using a reference angle of pi over 4 here, we'll recognize this angle to be 7 pi over 4. Therefore, the complete solution, that is, every solution to this equation can be expressed in the form pi over 4 plus 2k pi. That expresses pi over 4 and any angle coterminal with pi over 4. In addition, we have 7 pi over 4 plus 2k pi. It's at this point that we can go ahead and divide both sides by 2, or we can visualize this as multiplying all of the terms in both of these expressions by 1/2. We'll obtain x equals pi over 8 plus k pi, again I'm distributing the 1/2 here, and 7 pi over 8 plus k pi. Understanding that k represents any integer, we've expressed every possible solution to this equation in this expression. However, we only want the solutions in one rotation around the unit circle. So we're going to identify those solutions. Clearly, pi over 8 is less than 2 pi, and 7 pi over 8 is also a solution. Now we can use our expression, which generates all possible solutions to this equation, to determine if there are more solutions in one rotation around the unit circle. So notice from our first expression here, we have pi over 8 plus k pi. If we allow k to be equal to 1, and I'm going to leave the pi off of my calculation here, if I take 1/8 plus 1, I'm going to obtain 9 over 8, or 9 pi over 8. Because 9 pi over 8 is less than 2 pi, it is also a solution to the equation. So all I did there was substitute in k equals 1. Now, if I substitute in k equals 2, and I think pi over 8 plus 2 pi, then notice the output is 17 pi over 8. 16 pi over 8 is 2 pi, so 17 pi over 8 goes beyond one rotation around the unit circle. So we can stop with k equal to 1. Now let's check out our second solution. We chose the first value, 7 pi over 8, as a solution within one rotation of the unit circle. We can think of that as allowing k to be equal to 0. If we allow k to be equal to 1, 7 over 8 plus 8 over 8 would give us 15 over 8. 15 pi over 8 is less than 2 pi, so it is also a solution in the unit circle. Again, we just set k equal to 1, and we use these formulas to generate the individual solutions. So in this case, the equation has 4 solutions in one rotation around a unit circle. Now, it can be easy to overlook solutions, so I always like to verify that I've gotten all of the solutions using my calculator. So let's talk about this. I'm going to go to y equals, and I'm going to graph the left-hand side of the equation. Notice everything is moved to one side, and it's equal to 0. So if I graph this equation, the x-intercepts will show where the solutions are, okay? Because notice I'm taking this and I'm letting this be a function y, and we're setting y equal to 0. If y is equal to 0, we're looking at the x-intercepts. Now, I'm going to set my window very carefully between 0 and 2 pi, and I'm just going to do this manually. So my x minimum will be 0, my x maximum will be 2 pi. And by the way, make sure that you're in radians here. Also, because my solutions are in multiples of pi over 8, I'm going to set my x scale to be pi over 8 so I can easily recognize my solutions. So notice in this interval between 0 and 2 pi, we have 1, 2, 3, 4 x-intercepts, and we came up with 4 solutions. Also, because we set the scale to be in multiples of pi over 8, we can verify that 1 pi over 8 is the solution, and then I'm going to count 2 pi over 8, 3 pi over 8, 4, 5, 6, 7 pi over 8 is an x-intercept. 8, 9 pi over 8, 10, 11, 12, 13, 14, and 15 pi over 8 is an x-intercept. So using the calculator, I know for sure I've covered all of the solutions, and I encourage you to use your calculator to double check your work. The overall process of solving this equation is similar to what we learned in the last lesson, but now we're getting specific solutions out of our formula for all solutions. Let's try example B. We have tangent of 3x minus 1 equals 0. So I'm going to isolate the trig function by adding 1 to both sides. We'll isolate the argument by taking inverse tangent of both sides, but I'm not going to isolate the variable yet. Let's go ahead and look at our unit circle and find all places on the unit circle where tangent is equal to 1. We know that tangent is 1 at pi over 4, and we also know that tangent is positive 1 at 5 pi over 4. However, with our tangent equations, we recognize that the solutions are pi units apart. So we can express all solutions to this equation as pi over 4 plus k pi. And as always, k is an integer. Now that we've expressed those solutions, we can go ahead and isolate the variable. And I'm going to do that by multiplying both sides by 1/3. We can see then that x equals pi over 12 plus k pi over 3. So I'm just distributing the 1/3 inside those parentheses. Now we're ready to identify solutions that are within 1 rotation around the unit circle. That is, they're between 0 and 2 pi. So if we allow k to be equal to 0, our first solution would be pi over 12 plus 0, or pi over 12. For my next solution, I'm going to allow k to be equal to 1. So I'm going to take pi over 12, and I'm just going to use my calculator, plus pi over 3. Notice I'm leaving the pi off of my calculation so that the calculator doesn't yield a decimal value. So we get 5/12, or 5 pi over 12, still within 1 rotation around the unit circle. Next, let's allow k to be equal to 2. So we're going to evaluate pi over 12, or 1/12, plus 2 pi over 3, and I'm going to calculate it as 2/3. So we end up with 3 pi over 4. We're still within 2 pi, or 1 rotation around the unit circle. So again, we let k be equal to 0 for the first one, k equal to 1 for the second one, k equal to 2 here. So let's let k be equal to 3. So we'll take pi over 12 plus 3 pi over 3, or 1/12 plus 1. 1/12 plus 12/12 is 13/12, or we could say 13 pi over 12. How do we know when to stop? We stop when the value is equal to or greater than 2 pi. So let's update k to be 4. So we're going to have 1/12 plus 4 over 3, representing 4 pi over 3. I'm just using my calculator for accuracy and swiftness here, and we get 17 pi over 12. Remember that 24 pi over 12 is 2 pi, so I'm going to keep going until I get either equal to or greater than 2 pi. Let's try k equal to 5. So we're going to have 1/12 plus 5 over 3, and that's going to give us 7 pi over 4. Now, if we allow k to be equal to 6, then we're going to add 6 pi over 3, or 2 pi. If I add 2 pi to pi over 12, then I have gone beyond one rotation around the unit circle, so we can definitely stop here. We have found 6 solutions in one rotation around the unit circle, but I want to be sure that I've covered all of the solutions. So I'm going to use a graph to make sure that I have found every solution in one rotation. So I'm going to graph the left side of the equation, tangent of 3x minus 1. Notice it's equal to 0 in the original equation. I can translate that into finding x-intercepts of this graph. Now, we already have our window set from 0 to 2 pi for x-min and x-max, but to make it really easy to recognize my solutions, I'm going to set the x scale to be multiples of pi over 12, because that's what my solutions look like. And then we can graph the solution. So let's count the x-intercepts. We've got 1, 2, 3, 4, 5, 6 x-intercepts, and we have 6 solutions. So that's a good sign. Also, because we've set the scale at pi over 12, I'm going to count a couple of solutions. The first one clearly crosses at pi over 12, and then we have 2, 3, 4. The next one's at 5 pi over 12. 6, 7, 8, then 9 pi over 12, which reduces to 3 pi over 4, so on and so forth. So we can be really confident that we have found all the solutions to that equation in one rotation around the unit circle. These types of equations do require a lot of skill. First of all, we're solving a trigonometric equation. Secondly, we're solving a trigonometric equation with a multiple of the argument, or a composition in the argument, and we're not only expressing the complete solution, but we're using that formula to generate solutions within a finite interval. So a lot is going on here, and this is going to take some practice. In example 4, I got some good news. We're going to find all solutions in degrees. So again, notice the grouping symbols. If we get 0 degrees for a solution, we'll include it in a solution set, but we will not include 360 degrees because it really duplicates the solution at 0 degrees. 360 and 0 are coterminal. So let's solve first for the trig function on example A. We can divide both sides by 2. We get cosine of x over 2 equals 1/2. Now we're ready to solve for the argument x over 2 by applying inverse cosine to the other side. Thinking about our good friend and visual tool, the unit circle, I want to find all the angles in one rotation around the unit circle in degrees with a cosine equal to 1/2. So clearly that is going to be 60 degrees. Recall that cosine is also positive in quadrant 4, so 300 degrees is also a solution. The complete solution can then be expressed as 60 degrees plus 360 degrees times integer k, or 300 degrees plus any angle coterminal with 300. So we'll add again a multiple of 360k. Now that feels good. We got some answers here, but we're not quite done until we isolate our variable. So I'm going to multiply both sides of all of these expressions by 2. Therefore, we have x equals 120 degrees plus 720 degrees times k, or 600 degrees plus 720 degrees times k, where k is an integer. We're getting closer, but we're not quite finished yet. Now, since we're working in a finite integral, we're going to choose only the values that are between 0 and 360 degrees. Notice only one angle is a feasible solution here, and that is 120 degrees. We don't want to add 720 to it because then we'd be beyond 360 degrees. And also notice 600 degrees, though it is a solution to the equation, is not in the specified interval. So we only got one solution in this case. To see this on your calculator, we would need to go back to radian mode. So let's, go to degree mode. We were in radian mode. I'm going to rewrite the equation, 2 cosine of x over 2. Now, notice I want this to be equal to 0 so that I can judge my solutions using x-intercepts. So I'm going to subtract the 1 that was originally on the right side of the equation over to the left side of the equation. Then I can work with x-intercepts. Also, let's set our window to go from 0 degrees to 360 degrees. And you can choose any multiple. I'm just going to go with multiples of 30 degrees for my x scale. And notice we get one solution in this interval. Counting in multiples of 30, we have 30, 60, 90, 120 degrees for the x-intercept. So that really helps to not only allow us to visualize the solution, but also to verify that we've got all the solutions in that interval. Let's practice that again in degrees. So on example B, the first thing we need to do is isolate our trigonometric function, and we do that by subtracting 1 from both sides. Then we're going to solve for the argument by applying inverse sine to the other side. Consulting the unit circle, and you don't have to draw it out. I just find it very helpful to visualize the solutions. We want to find all the angles on the unit circle with a sine value of -1. And there's only one location. It's 3 pi over 2, or in degrees, 270 degrees. So we can say the solution x over 3 is equal to 270 degrees plus any multiple of 360 degrees. Remember, I'm starting by finding the complete solution. Then we are going to solve for the variable x by multiplying all of the parts by 3. The formula that generates the solutions is then 3 times 270 degrees, which is 810 degrees, and 3 times 360 degrees gives us 1080k. Notice, even the first solution for k equal to 0 is larger than 1 rotation around the unit circle. So there are no solutions of this equation that are between 0 and 360 degrees. Now, be clear that you understand this equation does have an infinite number of solutions, but there are no solutions in 1 rotation around the unit circle. Now, remember, this 270 degrees was the value of x over 3. When we solved for x, we got 810 degrees. So no solutions of this equation on 1 rotation around the unit circle. If you were to graph this on your graphing calculator, you would simply observe there are no x-intercepts between 0 and 360 degrees. All right, in this lesson, we're going to consider one more type of composition. In my opinion, this one's a little more challenging, but in example 5, we're going to find all solutions in 0 to 2 pi for each equation. So we're back to working in radians. Again, notice the grouping symbols will include 0 as a solution, but we're going to stop short of 2 pi. Now, what makes these equations different is the argument. Previously, we were dealing with a multiple of the argument. Now we have either a sum or a difference in the argument. So it's going to change how we handle the very last step. But we're going to start the same way. Number 1, isolate the trig function. That's done on example A. Number 2, isolate the argument. So we're going to apply inverse sine to both sides. And we end up with x plus pi over 4 equals inverse sine of 1/2. Now, before I deal with that pi over 4, I'm going to evaluate inverse sine of 1/2. And we'll do that by locating the angles on the unit circle in 1 rotation, which have a sine value or a y-coordinate of 1/2. Observe that sine is equal to 1/2 at pi over 6 and 5 pi over 6. So we can go ahead and express our complete solution for the argument. X plus pi over 4 is pi over 6 plus any angle coterminal with pi over 6. We express that as adding a multiple of 2 pi, an integer multiple of 2 pi. And we'll do something similar with our 5 pi over 6. Now here's where it gets a little bit different. We are ready to isolate the variable x. So we're going to do that by subtracting pi over 4 from both sides. Observe I do have 2 expressions on the right side to subtract pi over 4 from. So when I subtract pi over 4, I not only have to remember to do it to both expressions, but I'm only going to need to combine it with the term that doesn't have the k in it. What's different here, if you glance back up to our previous problem, recall that whenever we multiplied both sides by 2, we had to distribute inside parentheses. We did that with both expressions. What's different here is we're not multiplying both sides by something, we're subtracting something, so we're going to combine like terms. This means I'm only going to combine that pi over 4 with the term without the k. Clearly, x is isolated on the left side, and because my brain is tired, I'm going to use my calculator. 1 over 6 minus 1 over 4. I'm using this to evaluate pi over 6 minus pi over 4. We're going to get negative pi over 12. And the 2k pi stays as is. Okay, next we're going to evaluate 5 pi over 6 minus 1 pi over 4. And I'll do the calculation with the fraction, leave the pi behind, and we get 7 pi over 12. And then 2k pi stays the same. Remember, that part was altered whenever we had a multiple angle equation. Our next step is to identify which of those solutions, using this generating formula, are between 0 and 2 pi. Now notice negative pi over 12 is less than 0. It's not in the interval, so I'm not going to include negative pi over 12 as one of my solutions. However, 7 pi over 12 is between 0 and 2 pi, so for k equal to 0, the only solution we're going to obtain is 7 pi over 12. Now, let's go back to our first formula. Let's evaluate negative pi over 12 plus 2 pi, or negative 1/12 plus 2. We're using k equal to 1 here, and don't forget k can only be an integer. We obtain the value 23 pi over 12. Remembering that 24 pi over 12 is 2 pi, we are really close to the edge here. Now, if we take 7 pi over 12 and we add 2 pi, it's going to be bigger than 2 pi, so it looks like we found our two solutions. But let's be absolutely sure. I highly recommend, especially if you're taking a test, to double check your work with the calculator. So I'm going to switch over to radian mode and go to y equals, and I'm going to type in close to the original equation, sine of x plus pi over 4. But remember, I want to set the function equal to 0 so that I can observe x-intercepts as my solutions. Now, I'm back to working in radians, so I'm going to set my x minimum to be 0 radians, my x maximum to be 2 pi radians. And I think a convenient scale to use would be pi over 12, since both of our solutions are multiples of pi over 12. So when we graph our function, we can observe there are two x-intercepts. We got two solutions, and we could carefully count in multiples of pi over 12 to verify the two solutions that we obtained. So we did a great job on that one. This is pretty technical stuff, so it's worth it to practice that one more time. On example B, our first step is to isolate our cosine function. So I'm going to add 2 square root of 2 to both sides, and I'm going to follow up by dividing both sides by 4. This isolates our trig function, and we can reduce the right side to see that familiar square root of 2 over 2. Next, we isolate the argument x minus pi over 2 by applying inverse cosine to both sides. So we need to evaluate inverse cosine of square root of 2 over 2 before we deal with that pi over 2 on the left. As always, I'm going to use the unit circle as a visual guide. Helps me to think of where cosine is positive, helps me to think about reference angles. Cosine is equal to positive square root of 2 over 2 in quadrant 1 at the angle pi over 4. And we also know cosine is positive in quadrant 4. The value of x is square root of 2 over 2 at 7 pi over 4. So it looks like we have two locations in the first rotation of the unit circle where cosine is equal to square root of 2 over 2. So let's go ahead and express our complete solution. Pi over 4 plus 2k pi and 7 pi over 4 plus 2k pi. K, of course, is an integer. Now we're ready to isolate the variable, and we're going to do this by adding pi over 2 to both sides, including both expressions on the right. Remember, you have essentially two equations in one, separated by this comma here. Also remember, it's only necessary to combine the pi over 2 with the part of the expression that does not have the k. We're simply combining like terms here. So x equals 1 pi over 4 plus 1 pi over 2. A fourth plus a half is 3/4. So that gives me 3 pi over 4 plus 2k pi. And 7 pi over 4 plus a half. I'm going to be lazy again. Stick that into the calculator and we get 9 pi over 4. 9 pi over 4 plus 2k pi. We have gone above and beyond here and found the complete solution to the equation. That is, this is a springboard for generating the infinite solutions to that equation for all positive or negative integers, but we only want the solutions within one rotation of the unit 1. Now we need to recognize, using this springboard or formula for all possible solutions to the equation, which of these only fits within 0 to 2 pi. So clearly on this one, 3 pi over 4 is within one rotation around the unit circle. However, if I add a multiple of 2 pi, that's going to cause me to rotate beyond 2 pi. So 3 pi over 4 is the only solution that I'm going to get out of that first expression. Now, this one's pretty tricky. Notice the second one, 9 pi over 4, that's bigger than 2 pi. We can think of 2 pi as 8 pi over 4. 9 pi over 4 is actually coterminal with pi over 4. So our solution, and let me write these in order smallest to largest, our solutions will be pi over 4 and 3 pi over 4. Another way to see that is to generate it from this second equation. Remember, k is an integer, so it's also possible that k is a negative integer. So if I take 9 pi over 4 and I subtract 2, that is minus 2 pi, we end up with pi over 4. All right, so how do you catch something like that? Well, you may not, but if you check it with your calculator, you'll be able to observe if you've listed all solutions in one rotation around the unit circle. And if you have more x-intercepts than solutions, then that would prompt you to go back and look for the other solution. So I'm going to type in the original function. Notice it's equal to 0, so I can work with x-intercepts. X minimum is 0, x maximum is 2 pi, and let's set our scale to be multiples of pi over 4. So if we take a look at our solution, at our graph, we have two x-intercepts. They are located at 1 pi over 4 and 3 pi over 4. So I strongly encourage you to use your calculator to double check your work. Again, this is a really technical section, so if you're challenged by it, remember that is normal. There's a lot to think about here, lots of potential for little mistakes. But the overall idea is to, number 1, isolate your trig function. Number 2, isolate the argument. Number 3, express the complete solution to the equation. Then, number 4, isolate the variable. And then finally, identify the solutions within the given interval. So, best of luck on this. Keep practicing. The more you practice, the easier it will become.